Go.
All right, if there's anybody still listening out there, we're going to talk about optimization and scalability. If you're there and you cannot hear me, say something on the chat. This talk is mostly about highlighting main performance and scalability bottlenecks and giving you some simple but I think efficient optimization strategies. What we're going to cover is serial code optimization. Where we're going to go over the optimization process in general, describe some compiler-based optimizations that you don't need to do because the compiler is going to do for you, and talk a little bit about manual optimization. Oh, thank you. Then we're going to move on to on-node optimization, and the difference between on-node and serial code optimization is that nodes have tons of cores these days, so you're going to have to deal with resource contention. You're going to have to deal with load balance even within a node. And then we're going to jump onto multi-node optimization, talk about different MPI strategies, blocking versus non-blocking communication, using bidirectional communication, playing around with the eager limit size, and tell you why you should never use collective communications. Well, never. As little as possible. So serial code optimization. The optimization process is essentially a time-constrained process. You could continue doing this forever. It's a circular process where you profile your code, you identify hotspots, places where your code is spending a large amount of time, a large fraction of the total execution time. Then you will try to modify those code sections to make it go faster. But then you need to test again, because very often you would have fixed the problem that you had in the code, but you might have introduced a different issue somewhere else in the code by fixing that problem. So don't assume that once you have one single profile of your code and you know where the problems are, by fixing those obvious problems in the first round, you're going to get a faster code. You always need to test your changes. Obviously, you can keep doing this forever, but at some point you're going to have to stop because probably your PI wants to see a publication or two out of this project, and you need to put time into producing results. So you should essentially take the optimization process only as far as you have to in order to get your results. If what you need to do is to get 2 or 3 results in 24 hours, once you can do that, you should really stop. Now, to do optimization, you need to understand the performance of your code. And for that, you need to learn a little bit about performance analysis. Now, in performance analysis, controlled measurements are essential. You're going to have to repeat your measurements because on a large shared resource, a single execution might not be representative of the average time that it's going to take you to finish a workload, simply because the network was flooded because 1 or 2 users were doing something they shouldn't have been doing at that time, and we don't have control over every single thing that a user can do. So repeating your measurements is very important. It's very important that you document what you did to do these measurements, because when somebody else comes to work into this project in 6 months or in 2 years, and you tell them, oh, this works better if you use this particular flag, or if you use this particular data structure, and they ask you, why? Well, because I did some testing. How? So you need to be able to document what you did and how you did it. In this regard, it's important that you try to automate all these things. It's hard for you to go ahead and every time you run something right on a piece of paper, I use this compiler, I use these flags, I use these environmental variables. Try to script all of these so that every time you run, you already collect the information automatically and you don't have to deal with that problem. Something very important, particularly when dealing with multi-core systems, when working with more than one thread, which most people will be doing in a system like Stampede all of the time, is to make sure you understand how the code is executing, in the sense that you need to know where your threads are being pinned, where your MPI processes are being pinned, whether they're allowed to float in a socket, they're allowed to just execute on a single core, etc. And I believe you saw some of these today when we discussed hybrid codes. But this is something very important. Now, let's talk about compiler-based optimization. There's a lot of not very sophisticated users that would just simply compile their code with the defaults, which tend to be -02, which is a particular compiler flag I will describe in a minute. Actually, increasing the level of optimization that the compiler is allowed to use for your code can help you improve your execution time significantly without you having to make any actual changes to the source code, which is a lot more time consuming. There is no universal flag set that is going to help every person out there, every code. But there's a set of flags that are pretty reasonable to use, and I will go over some of those later. If you want to dig a little bit more into this, there's plenty of documentation from both Intel and AMD on how to optimize for their architectures. And you have a link there to an Intel document, but you have similar products from other companies. Now, the first thing I like to describe is the types of compiler options that you have in terms of functionality. You have options that will give you additional information apart from the usual messages you would see on the screen, options that change the optimization level or how aggressive the compiler can be doing changes to your source code before producing the binary. You can specify architectural flags, and you can also enable interprocedural optimization. Now, the information part is really critical. In particular, if you're working with systems that are sensitive to vectorization, or if you're getting results that you don't really expect in terms of the performance, because then you can produce an assembly listing of a particular function, and then you can see what blocks the compiler has created and try to figure out if they make sense for what you were trying to do. Which probably you don't want to do all the time because that's time consuming, but it's worth for small sections of code that are critical in your critical path to look at that. Now, some useful options in Stampede would be -03, which is the optimization level, tells the compiler how aggressive it can be in the changes that it can make to the code. -IPO, which enables interprocedural optimization. And what that wonderful word means in this context is that the compiler is able to optimize across files in your compilation. So if you're building a program that has 72 different files and multiple functions in each file, the compiler is able to do optimizations across files and across subroutines to try to get the most out of your code. If you don't use IPO, it would only restrict its optimizations to a function or file level. Then there's an architecture specification, XABX, which is the highest level of extended instructions that the Sandy bridge in Stampede supports, or that you could change by -X host, and it would have the same effect. It would look at the chip ID and shows the highest possible instruction set, the more advanced instruction set supported by the processor. By the way, I'm using the Intel C compiler for the example, but these options remain the same for both Fortran and C++. If you're running threaded code, with Intel, you would have to use the -OpenMP flag. With GCC, you would have to use -F OpenMP. And you can add these flags, OpenMP report and Vec report, to obtain OpenMP and vectorization information. Vectorization information you can always obtain independently of whether the code is threaded or not. This is just an example because those options just happen to fit nicely in one line. But what this will do is this will produce more verbose output telling you which sections of the code were parallelized according to your pragmas, what sections of the code were vectorized, what loops were vectorized, and if they were not vectorized, why. In some cases, this is because there's a call to an external function that is impossible to vectorize. In some cases, it's because the compiler believes there are not enough iterations in the loop to make it worth sending to the vector unit. And I just talked about vector units, and I didn't tell you what vectorization was. But if you bear with me, in about 2 minutes, I'm going to describe what a vector operation is, so that you know what I'm talking about. Additional information can be obtained through the OPD report option, which will tell you a fairly large amount of information, most of it incomprehensible. But if you're patient, you might be able to get some interesting information from this. It will tell you things like, I have fused these two loops, or I have split this loop, I have unrolled this loop to this depth. So it tells you fairly high level of information, but in a good amount of detail. Whenever I use that OPD report option, I specify an OPD report file because the output tends to be too long and verbose to just look at it in the screen. Now, regarding these optimization levels that I've mentioned O2, which is the default. I've mentioned O3, which is essentially optimize for speed and enable relatively aggressive optimization. The compiler user guide will tell you that this may alter the results. In most cases, this is not the case. It may alter your results because it will do things like use an approximate division. It will do things like use sometimes on a smaller number of bits for storage of intermediate results. But typically, you shouldn't see a change in your results. And if you do, there are ways to improve the precision of the calculations with things like minus FP model, precise, and so on. Now, typically, all compilers default to minus O3. In some cases, particularly if you have code that is very branchy, does very little things, mostly integer operations on tons and tons of small loops and branch, then O1 is probably better. But in most cases, O2 works well. Sometimes people see minus fast and they think this is a great thing, and it would, other than it actually contains these 5 options: O3, X-host, IPO, no precision division, and static. And the problem is that the static option is not fully compatible with our MPI stacks, so you should not use this option attack. Please use minus O3, X-host, IPO, no preg-div, but remove the static from the compilation line. And like I said, keep in mind that for most scientific workloads that have a big fat loop with most of the math happens, O3 tends to be the best, but if you have very branchy code, O1 might actually be better. Now, I jumped the gun a little bit and I talk about vectorization and extended instructions without saying what they are. And there's no reason why you should know what they are. What a vector instruction is an instruction that is executed over multiple data at the same time. It's a single instruction, but it executes over multiple data. What that means is that you can get several operations effectively done on a single cycle. That's not really quite true because there's a certain latency into setting up the vector operation, but for the timing, let's just assume that it just happens magically in a single cycle. So there are several types of extended instructions, and this pretty much started with MMX, then went to SSE, which is 128-bit wide, but only applies to single precision data. And what we have today is ABX for Sandy Bridge, or ABX2 for Haswell, and the Mike 512 instructions. Now, the reason vectorization is much more important today than it was, say, 5 years ago, is because 5 years ago, all the support we had was for 128-bit vector operations. That's essentially 2 doubles. So if your code is double precision and you vectorize it really well, the maximum you're gonna get is a factor 2 improvement. Now, it's almost impossible that all your code is going to be vectorizable. None of your I/O is going to be vectorizable. There's a whole bunch of stuff that you cannot vectorize. So the most you're going to be able to get out of this, a factor 1.5, maybe 1.2. So most people didn't consider this worth the effort of changing their code to be vectorizable, because for 20% improvement in speed, I'm not going to spend several man-hours changing the code. It's just not worth it. Now, today we have potentially a factor 4x speed up in Sandy Bridge and 8x speed up on a mic on a Xeon Phi coprocessor. So it's definitely worth looking into vectorization. And this is why I dedicate a couple of slides to this. I think if you're not familiar with the concept of vectorization, it would be something that I think it's important for you to invest a little bit of time, look at these Beck reports that I've mentioned earlier, and see if there are sections of your code that don't vectorize that you could vectorize better. Otherwise, you're going to be leaving between 3/4 and almost 90% of your possible flops out of the equation when you compile your code, depending on whether you run on the host CPU or on the FICO processor. This is just an image to reiterate what I just mentioned. You essentially, with SIMD or vector instructions, what you have is a single instruction that is executed on 4 or more processing units simultaneously on different pieces of data. Now, performance libraries. One of the best things you can do in order to improve performance is to not write your own code. I know that sounds funny, but if a large group of people has spent 20 years working on an optimized version of a matrix multiply, you're probably not going to do better than them in 2 days. So if you can use an optimized library, you should. So it's always worth spending a little bit of time at the beginning of a project, thinking about the algorithms you're going to use, see if there's something out there in open source, or not open source, but provided by the center, like we provide the MKL libraries that you could use to improve the performance of your code. This happened to me several times that people say, hey, but I'm using the numerical recipes book and there's this algorithm that is fantastic. And that's okay. That's a good implementation, but that book is mostly designed to teach you how the algorithm works. It's not designed to provide a very high performant implementation. So don't think that something like numerical recipes is going to give you super optimized code. It's going to give you something reasonable, but it's going to be significantly far away from what an optimized library is going to provide. Very relevant to tag are the Intel math kernel libraries, which cover a lot of the linear algebra you might want to do, plus 1, 2, and 3. FFTW, both 2 and 3, and the PETC set of libraries. And we probably have a ton of others that I haven't mentioned, but these are some of the most highly used ones. And I have a single page about best practices. And I think the most important line here is that premature optimization is the root of all evil, like Donald Knuth said, and for once I think he was right. Essentially the idea is don't try to make your code too clever. The compiler is capable of making extremely complex transformations to your code to make it faster. Just make clear and simple code so that the compiler understands whether there is a dependency between 2 operations or there isn't, and so it can make the right transformations. Typically, if you write code that another human being might be able to understand, the compiler should be able to understand and then make the right choices. There's obviously things that you should always try to do. Things like access memory in the preferred order. Any of you that program in either C or Fortran will be aware that there's a preferred accessing order in either language, which is opposite. And so if you get it wrong, you're going to spend a lot of time trying to access memory just because of the way the cache is refilled with data from memory. Now, try to minimize the number of complex mathematical operations. That sounds silly, but the computers are really good at doing plus and an addition and a multiplication, but they're not so good at doing things like exponentials or sines or cosines or square roots. So if you can define one of these operations once because the result is going to be a constant and then just reuse the constant, you should do that. That's something that the compiler will typically catch and do for you. But if you do it yourself, you know it's always going to be there. Excessive program modularization. I'm all for modularization. I like to have things separate in separate functions and separate files, but you can take things too far. And at some point, if your encapsulation has too many layers, the compiler is unable to optimize anything because it's unable to follow up what depends on what and how things are related. So if you take modularization too far, or encapsulation more than modularization too far, the compiler is not able to write properly optimized code. Typecasts and conversions of type, they you might not be aware, but these are very expensive operations. So try to avoid it as far as you can. And minimize the use of pointers. And by this, I don't mean don't use pointers. If you're writing C, you have to use pointers. The only way to write effective code. But don't write them in places you don't have to. Because when you have a pointer, when you have a dynamic allocation, the compiler has no idea what's going to come after that pointer. There's no additional information the compiler has during compilation time to know what it's going to be able to do with that array. And so it's not able to do any particular optimizations regarding that data structure. Things to avoid within loops. Actually, most of these can be fixed by the compiler during compilation time. If you have constant expressions that are evaluated again and again and again in a loop, the compiler will remove that, put it outside the loop, and just reuse it inside the register. Branches and conditional statements. The compiler is sometimes able to get these out of a loop, but not always, because sometimes it requires a major restructuring. And function calls and I/O operations, in particular, opening and closing files inside the loop. Unless you have a very good reason to do it, you shouldn't, because on a shared parallel file system like Lustre, operations such as open and closing files are very expensive because they go through the single metadata server that serves the whole cluster for every file system. And so that's really a major bottleneck. Now, in terms of code optimization, again, from a fairly high level, which is pretty much what we can do in less than an hour, try to improve memory usage. And trying to improve memory usage, what that means is not only write your access in the right order so that you're not going against the row major or column major ordering or of the language that you're writing the code in, but very often it's faster to recalculate an element that is already on a register than to go to memory and grab an old copy that you had from God knows when at the very beginning of your code execution and then reuse it. So think about if you can recalculate something in a single line of code, often that's better to accessing a variable that is old and is no longer on a register. If the variable is being used often and is in a register, there's no point in recalculating it, of course. Now, allow the compiler to unroll, fuse, fission loops. This is something that you typically do by default, unless you specify something with a pragma. But the compiler is actually pretty good at finding loops that should be fused because they have a very similar range, and so it avoids the overhead of an extra loop, for example. And minimizing stride. This always helps for the simple reason that when the runtime brings data from memory into cache, it brings it in lines of 64 bytes. So it never brings a single double precision element. It brings 8 at a time. If out of those 8, you only use 1 or you only use 2, then you're wasting a lot of memory bandwidth. So having a unit stride really helps both reducing memory bandwidth and also helps the code being able to vectorize sections of your code. Because vector operations only really occur on contiguous elements. And either your elements are already contiguous or the compiler has to make multiple operations to put them into an array so that they are contiguous. And both things take a significant amount of time. If you write your loops so that the iterations are independent, and very often you can, but every now and then you write the code in the first way that comes to your head and you introduce a fake dependency. If you write loops with independent iterations, then you will be able to take advantage of vector units and of extended streaming SIMD instructions. This will allow you to do multiple operations per cycle. The last one should be obvious, but sometimes people forget. Reducing I/O is particularly important in large systems like Stampede, where you have a large parallel file system that is shared by multiple users. If you're only using one node, you're writing to a parallel file system, your throughput is not going to be as great as if you were in a single workstation with a large RAID. On the other hand, you also have lots of other users that are doing I/O simultaneously. And in any case, I/O is the slowest part of your whole execution. So try to minimize I/O as much as possible. Some applications come with defaults that are extremely short. They tend to be very verbose. They tend to dump information every 1 or 10 iterations. Very often, that's really not necessary for you, particularly if this is not an interactive job that you're monitoring. So please pay attention to that. And I've talked a lot about memory and improving memory usage. And just to give you an idea of how expensive it is to get data from memory, this is a slide with some speeds and feeds for a Sandy bridge in a Stampede. And what I would like you to notice is that if you have to go out all the way to external memory, to the DIMMs, to pick up a piece of data, the time that it takes to get that data down to a register where you can actually use it for an operation is equivalent to doing about 3,000 floating point operations. So when I said you need to really use memory better, don't dismiss it as a, well, sure, I need to use memory better. No, this can make a difference of orders of magnitude in the performance of your code. Because every time you go to main memory and you're not utilizing the cache hierarchy properly, you're wasting a lot of potential compute power. Particularly if your code is stalling on that particular operation. Now, I have a couple of slides here that are essentially just for illustration purposes, and in this one is just to remind you what the correct order in access is for C and Fortran, so that you have it as a reference when you're writing code. If you don't remember, you can go to that slide. If you write the access on that order, you should get the better performance. Now, talking about procedure inlining, this is something that the compiler will do for you. You're not going to do procedure inlining on your own. What it actually does is, if the compiler detects that there's a function call that is, the function itself is pretty short, but it's called many, many, many times. In order to reduce overhead from calling that function, it will just copy and paste that function in the middle of your loop. It will remove completely the function call. The function will not exist in assembly, and it will just be embedded in the middle of your code, as you see on the right-hand side. This is called procedure inlining, and typically most compilers will do it automatically until your binary grows to a certain size, and then they will stop. So if you want to make sure that a particular function is inlined, you can always use a pragma to suggest to the compiler that it should be inlined. Otherwise, if it gets too far into the code and the compiler has decided that it's not inlining anything anymore, the most important function in your code that you really wanted inline is actually not being inlined. Loop unrolling is something that the compiler does very, very often just to be able to do multiple operations per loop, multiple operations per loop iteration. And as you can see, it's very simple. It will essentially just use offsets to access 2, 4, 8 elements on an array for every time a loop iteration. This is something I would not recommend you do manually because the compiler is really good at doing this anyway. And this is very similar to what a compiler will do in order to vectorize a loop. It would also grab several elements, put them in the vector unit, and so every time it goes through a single iteration, it will do multiple instances. Loop fusion is essentially the union of two loops that had identical ranges or similar ranges, where the compiler decides, well, I'm just going to fuse these two loops because they loop over the same exact elements, and there's no dependency between the left-hand side on both operations. So I can safely put them inside a single loop and save overhead from the second, which the overhead from the second loop was probably small enough that it wouldn't matter, but it's always interesting. Now, reblocking is a little bit more interesting. Yeah, is there a question?
So it's more of a comment. So when you're writing your code, if you're writing your own code, try to set up your loops so they don't have data dependencies.
Yeah, that always helps for several reasons. For both loop unrolling, for loop fusion, it matters only a little bit. For loop unrolling and vectorization, that's critical. If you don't have any dependencies, so A of I does not depend on A of I minus 1, that kind of straight dependency, then the compiler is really good at either unrolling the loop or putting it into a vector unit. Yep. So in the case of array blocking, what we're trying to do is we're trying to block a number of operations that are going to possibly reuse data. The intent of this is that that data is gathered into either L2 or L1 and then is reused several times before we let it go and we access the next block. This is the way that most matrix multiplications are written, with at least 2 or 3 levels of blocking. An example of what that actually looks like for a square matrix would be this, and essentially the only thing that is interesting here, and I bet that's not going to show, that's great, is that essentially if you have an IJK structure, you're now going to have 2 loops for every index. You're going to have, in this case, K and KK, J and JJ, I and II. And one of them is going to go from 1 to the total number of elements in the matrix in a certain block size step. And the other one is just going to fill in that block size from whatever initial point we are in to the very end of that block. And that's an example of performance. Wow, and that's really old. This, I don't even know where this is from. This must be Ranger. Okay, so that slide needs to be updated. But essentially, you can see that there's a huge difference in performance between a non-blocked matrix multiply and a blocked matrix multiply.
Will the compiler do this for you in certain situations, if you're not using the optimized libraries?
Not that I know. As far as I know, the compiler itself won't do it. There is automatic code generation frameworks that will do this for you, but not the compiler itself. But if you use MKL or PETC, you're definitely going to get this kind of, actually, better than this. This is a very simplistic example, but you get a very nice, and typically things are blocked mostly for L2, but we're getting to the point that the processors, they have so many cores, they're so fast in their throughput, like Haswell is so fast in its throughput, that it needs to add a 3rd level of blocking even for L3. So that was all I wanted to cover for general optimization, single thread, and now let's talk a little bit about on-node optimization. So a prototypical node will have, in HPC, typically 2 sockets, each of them with multiple cores, each of them with multiple channels that access memory, each of them connected to the PCIe Express bus, and through that bus talking to either an accelerator or a network interface. Each of these has a different bandwidth, a different latency. Here I've gone from green to yellow to orange to red. So this is getting worse as we move from memory to socket connection to PCIe and to the wall, right? Or to the rest of the cluster. So the typical bandwidth of some of these things, this would be about 78 gigabytes per second. This is probably about 40 plus. This is less than 7. And this is about 6.2 gigabytes per second. So things degrade very, very quickly. So basic scalability issues when talking about single node. Resource contention effects, because we have a shared L3 cache and everybody's trying to read and write to that shared L3 cache. That L3 cache is probably 8-way associative, and you might have up to 16 or 20 cores writing to it, so you can run into problems. Shared DRAM access, so all these cores are sharing these 78 gigabytes per second access to memory, so the bandwidth per core is actually not that great. It actually hasn't changed in many, many years. If anything, it's gone down. You have prefetcher. Every core has use a prefetcher, but at some point you have so many streams in flight from all these cores that you might not be able to prefetch appropriately, and the prefetcher will just completely give up, or just prefetch random stuff that doesn't really help you at all. So things are much easier when you have a single thread, but when you have multiple threads, contention becomes a real issue. Bandwidth issues, just essentially because you're going down from the 78 gigabytes per second of memory to having 7 gigabytes per second to transfer to a GPU or a mic. And very often that transfer is not even as effective as it should be, so you might not be able to get even the full bandwidth. There's ways to minimize this, and the best way that I know to minimize this effect is first transfer as little data as possible, which is always very easy to say, but not so easy to do. And second, use asynchronous exchanges to make sure while the data is in flight, each of the devices still processing some data, and you don't completely waste your time being held while the data is exchanged. Sometimes that requires partitioning your computational domain in a slightly different manner, perhaps into a boundary and a core, or perhaps into a top half and bottom half. Everyone has a way to do this. But the important thing is that you're aware of these particular bottlenecks that appear when you're working on a node as opposed to a single core. Something to keep in mind is that best single thread performance is not always the best on-node solution. And the reason for that is that while the prefetcher may have been capable of prefetching correctly for your 56 streams from a single thread, which it's not going to be the case. But say you have 16 streams, you would probably be doing pretty good. When you multiply 16 by another 16, now you have 256 streams in flight, the prefetcher is going to give up. So you might have to rearrange your code so that you have less streams in flight from every thread. And that's just a simple example, but there's many other examples. For example, cases where recalculating an element wasn't worth it with a single thread might become important when you have multiple threads all trying to access memory to get hold of that element. If each of them just does a calculation in parallel independently, you're probably saving time. So these are things that are worth revisiting when you're doing on-node scaling tests. Additional issues that are reasonably hard to get rid of are serial sections in the code, particularly startup and shutdown sections of the code. Here, there's often either a data dependency or an I/O operation that is hard to parallelize. So if we can get rid of this, that's great, but sometimes it's hard. Imperfect load balance, that's pretty common, but it's most of the time due to an uneven static decomposition at the very beginning of the execution, or is due to a local change in the local workload. And that can happen if you have, say, an automatic mesh refinement system or something like that. And there's ways to fix imperfect load balance, but they all require that you put a little bit of work into dynamically checking what the load is on every one of your tasks and fixing it. And there's libraries that allow you to do this without having to write your own code. Imperfect process or memory affinity. This is probably the most common reason I see for code that underperforms. Somebody forgets to pin their threads appropriately or unpin them in some cases. And so they have 16 threads running all on a single core. And they say, hey, my code used to work much better. Now it's 20 times slower. And then you look at the execution and you see that somebody was using Mbappage 2, but they didn't use stack affinity. Well, the default for Mbappage 2 will be to put all the threads on the first core it finds, and that's not good for you. Other issues that you're going to start to see as soon as you have more than one process are going to be communication issues. And these can be implicit or explicit. Implicit in the sense that if I have an OpenMP code, I'm still going to have communication issues because I need to have synchronization points, and those require communication between the threads. Implicit if I'm using MPI or I'm writing explicitly an OpenMP barrier, because then I'm asking for a synchronization. Now, talking about processor memory affinity, and I think you must have seen some of this morning when when we talked about hybrid code and when we talk about OpenMP. So I'm not going to spend a lot of time other than saying this is an important bit for performance. If you're not pinning your threads, you don't really know how your code executed. So it's very hard to make a judgment call on the performance of a code when you don't know exactly where everything executed. The tools are there. You can use NUMA control. You can use task set. You can use KMP Affinity, which is probably the easiest way for most users. It's just an environmental variable that you can set. And I have 3 examples here. If you export KMP Affinity to be compact and you had a 4-core system which can execute 4 threads per core, and you had only 8 processes, this is what the layouts would be with compact, balance, and scatter. And I should mention that balance only works in the FICO processor, but compact and scatter will work on the Sandy Bridge host. So always set affinity, or use stack affinity if you're using the Mbappage 2 MPI stack in Stampede. That's going to ensure that most of your memory accesses are local, the threads are not dancing around when the OS wants them to dance around, and overall your performance should be better. Saying that you could see after a factor 2 performance is an exaggeration, because that would really mean that you have all threads running on socket 0 and all your memory allocated in socket 1, which would be a very uncommon occurrence, especially because by default, Linux operates on a first touch policy, and so the first time that a thread touches memory, it should be allocated locally to that thread. And it's very strange that you would end up with a weird situation with all your memories in one socket and all the threads are in the other. But still, it's definitely important to set affinity whenever we're talking about optimization and performance analysis. And affinity is probably the most important thing on node. So once we're done with the node, we need to think about what happens when we want to run on more than one node. And what happens when we want to run on more than one node is that we need to look at a different set of issues. The main question that I pose myself when I'm thinking about scalability is, how many CPUs can I use efficiently? I mean, any of my codes can use all the CPUs in a Stampede. That doesn't mean that they're going to use them effectively. They might be running at 0.01% of the maximum possible performance that I can get, just because they might not scale that far. So it's important not to waste your own resources, and it's also important that if you want to solve larger, more complex problems, your code needs to be able to scale properly. There's 3 typical tests that people describe. We have a strong scaling, weak scaling, and essentially time to solution. With the strong scaling, you're looking at a fixed problem size that gets distributed amongst an increasingly larger number of processors. With weak scaling, you have a fixed problem size per process, so per MPI task. So your problem grows up in size with the number of MPI tasks. And fixed time to solution is essentially you keep increasing the size of the problem, you keep adding nodes, and you see how many nodes you need to keep adding to get the same time to solution. That one is more complex and sometimes not so useful, but there's a fair amount of tools available to look at scalability. You can use MPI or inline timers if you're so inclined, but if you're working with a very large code or a code that is not yours and you're not an expert, this is pretty hard because it requires you to do a lot of hands-on coding. There is tools like MPIP and IPM that are available in Stampede and will give you a summary of MPI communication. They're fairly simple to use, but the information they give you is pretty much limited to number of executions of a call, the message size, and the time. So they don't tell you anything else about the system. They're just focused on MPI. Then you have things like prof or gprof, which even for MPI codes might be helpful because you could dump a profile per MPI task and you could see at the different times spent on different functions. That will help you see if there's a significant workload imbalance between the different tasks. And then there's the more complicated tools like HPC Toolkit, Tau, or Scalaska. that can really give you a ton of information, both about MPI and about hardware counters and about very low-level execution detail, but are typically a little bit more complex to use. And so if you're just looking for scalability data, something like MPIP or IPM is going to be more useful than a very large application that gives you other information you might not need at this point. Now, I like to divide communication bottlenecks into bandwidth limited communication, latency limited communication, and others. And the others is a very large box. But essentially, bandwidth limited communication, you have large amounts of data being exchanged with every message, but your algorithm is not completely data local. This is a problem that is very hard to fix because you're already writing the highest MPI bandwidth possible. So to improve your communication, you need to find a way to either reduce the data exchange, and that might mean taking your code into a hybrid implementation where you use OpenMP in the node and then MPI across, or changing completely your algorithm. And sometimes that's not feasible. So bandwidth limited communication, if you have that problem, you're already doing pretty good. Latency limited communication tends to be more a result of implementing a solution to a problem in the way that you would do it in paper, in the sense that, oh, I solved this little thing, I exchanged that data. I solved this little thing, I exchanged that data. Instead of, I can solve these 25 things and then exchange 25 elements in a single message, which is more what you would think if you've been doing computation for a while. So latency limited communication very often has a simple solution, which is you calculate several things on each process, then you pack them all in a single array, you exchange them. So your exchanges are larger but less frequent. The others box is huge, and I don't really have enough time to go into it, but I just like to mention because it's really important that you're aware of this. Unbalanced workloads, the same problem that we had on single node execution, where multiple threads could have, or even multiple MPI tasks. You have a workload imbalance. This happens to even a larger scale in distributed applications because your network is even slower. So any imbalances are going to show more strongly than when single node execution. Excessive I/O. This is always a problem, but when you have tons of tasks, you can create much larger problems for the file system. So if you were hammering the metadata server with 4 or 8 tasks on a single node, and now you try to execute on 500 or 2,000 nodes, then you could bring the system to its knees. And nobody's going to like you if you do that. And the performance of your code is going to be terrible too. So it's not only about being a good citizen, it's about being clever about the way your code is executed. This is an example of a strong scaling for a code that didn't really scale very well. Actually didn't scale very well at all. So you can see that initially the execution seems pretty nice. It's a little bit over the linear term, which means the code can be further optimized for single thread. But when you hit about 128 processors, your parallel efficiency is reduced to 60% approximately. In fact, after that, the communication takes more time than the actual execution of the code, which is why your speed up factor starts to go below 50% of the number of cores. So if I was this person running this code, I think I would run at 64 cores unless I really need those results. And then I would never run at over 128 because if I run at a larger scale, my time to solution would be even longer. Right? Which is something that some people don't realize, that this is not a curve that flattens. This is a curve that goes down. It's like a inverted parabola. So you keep adding processors and there's more and more communication and they have nothing else to do. So the point of this figure is to ask you, when you're starting to run on a large system like Stampede, to do a few tests with a characteristic problem size. Maybe a reduced execution time, maybe a slightly reduced problem size, but the same problem size per task. And you run some scaling tests to see what's a good size for you to run, so that you know what's more efficient for you and what makes more sense in terms of the service units that you can use in your project. Now in MPI, there are several ways to communicate, and one of the main differences between two classes of communications is whether the messages are blocking or non-blocking. Blocking messages prevent the process that executed the call from doing absolutely anything else until that call is finished. The only thing it can do is poll for whether that call has been completed on the other side of the communication. On the other hand, non-blocking calls allow the task to do something else until it receives a signal that the message has been completed. And what this allows you to do is it allows you to overlap part of this communication with some work that you might have to do, either loading data from memory, executing floating point operations, whatever you need to do. Now, the way that works is if you were doing blocking MPI communications, you would have, say, your compute kernel execute, and when it's done, you're going to exchange some data, and you can do nothing else. If you were distributing this into two different kernels, one that takes care of the boundaries, then you can exchange those boundaries asynchronously while you compute the kernel core on both tasks simultaneously. You would complete your MPI communications, and then you would have saved some time by overlapping the communication with the computation of the other kernel. You wouldn't save all the time, so this line is purposefully not aligned with that one because you still have some overhead in setting up these two different sections of the code, and you still have some overhead in completing the asynchronous calls, but you would still save a significant amount of time. So the advice here is if you can, try to use non-blocking communication or even better, one-sided exchanges with MPI2 or MPI3 calls. Particularly if you have fairly large message sizes, that tends to be pretty beneficial. Now I want to talk about bidirectional exchanges, and that's something that the InfiniBand network allows you to do. A typical case is we're solving a problem on a grid, and we have 1 or 2 or 3 layers of ghost cells that we're going to update our neighbors with, maybe because we need to do a gradient or because we need to do a Laplacian, and so we need to know 1 or 2 or 3 of our nearest neighbor cells, right? So on every time step, we're going to do some computation, and then we're going to do a data exchange, and every task is going to exchange with its neighbor. So this can happen in 2 ways. You can do it with an MPI send, an MPI receive, and then an MPI receive, and an MPI send on the other side. And that doesn't overlap anything. That's just standard one-way communication. So don't do that. Or you can do this with an MPI send, MPI receive on both sides, and then use an MPI wait all to complete the communication. Now, in the second case, when you use asynchronous calls, both messages are going to be traversing the wire simultaneously, which means that you can almost get twice your usual memory bandwidth. And so this is a test I ran a couple of days ago in Stampede with the default Mbappage stack. And if you use this first example up here, when you do a send and a receive, the maximum memory bandwidth you can get is about 6.2 gigabytes per second. However, if you were to run in bidirectional mode with I send, I receive, for the same exact amount of data, you can get almost 12 gigabytes per second. So it's not quite a factor 2x, but it's a factor 1.85 or 1.9. So whenever you have any of these regular exchanges of data, if you were using MPI send receive because it's just simpler to implement, you should probably consider going to an asynchronous mode just to use this feature of the InfiniBand network. And now I mentioned very early on that I would talk about the Eager protocol and the Eager limit. Now, I've talked very, very little about MPI. I've essentially assumed that you know something about MPI. But you had somebody else talking about MPI this morning for quite a bit. So I don't think, I don't know if it was described to you how MPI actually matches messages. So MPI can use many different protocols to match messages. I'm going to talk about 2 that form the basics of everything else. MPI can use the Eager protocol, where the data that you want and a small envelope are sent all together. This is why it's called eager. It's just sending everything. It's getting rid of everything. It's like, okay, here you go. This is your message. I don't want to have anything to do with it. This envelope has information about the message itself. So how long the message is, what type, what's the source that is sending the message, what's the target that is supposed to receive the message. It's a very simple envelope. It's very short, pretty small. We also have the rendezvous protocol, which sends the envelope first. It waits for an acknowledgement that the remote process is ready to receive the data. Then it sends the data and the envelope. And then it receives the envelope back as a signal that all the transaction has been completed. So as you can see, the rendezvous protocol is has a little bit more overhead because it needs to set things up and so on. But you still need it, because if you were only going to do eager protocol, you could only queue up so many messages before you run out of buffers in the system. You would require way too much memory to provide system buffers for all the data that has to be in flight. So what we do, and what the MPI developers do, is they typically use an eager protocol for small messages, and at some point between 12 kilobytes and 256 kilobytes, depending on the implementation, you will switch to a rendezvous protocol to avoid running out of memory. So eager is always a little bit faster, it provides a little bit better latency, but rendezvous is always usable. And the key is that you as a user can switch where the eager limit lies. So you can switch it from 12 kilobytes to 256. Now you have to think that when you do that, your MPI execution is going to take a lot more memory than it used to before. So you have to be careful. But what you can do is you can gain a significant amount of bandwidth, particularly if you're running on an intermediate message size. Say that you're running with a message size that is 64 kilobytes and you're using Mbappage. Mbappage by default has an eager limit that is below 64 kilobytes. So you should be able to improve your overall bandwidth for your code by switching the eager limit to, say, 92 kilobytes or 128 kilobytes. That means it's going to take a little bit more memory, but overall it might be worth it. This is something that users of not VASP, of NAMD typically find useful, just to switch the eager limit to a little bit higher value than the default. Something that we don't normally mention because we have it enabled by default in Stampede, but if you are running in a different system, might be useful to you, so I want you to know about it, is that MPI stacks have several ways of optimizing exchanges that happen within a node. So messages that don't necessarily have to go over the network, because they're messages between core number 0 and core number 2, which are in the same socket, for example. There's shared memory, which goes through shared memory instead of going over the network, but still that's a double copy of the message that needs to be sent. There's the loopback device, which does 2 direct memory access operations. And then there's the kernel-assisted libraries like Limic, KNM, and CMA. In Stampede right now, we support both Limic 2 through the default Mbappage 1.9 A2 stack, and CMA through the newer Mbappage 2 2.1 stack. By default, we have them enabled, so there's nothing you have to do to take advantage of them, but I want to show you the difference that it makes. On the left-hand side, you see a figure for Limic 2. If you disable Limic 2, you will get the blue line, and so your maximum on-node bandwidth would be about 8 gigabytes per second, which is pretty nice, significantly higher than the network bandwidth at any rate, which is 6.2. But if you enable Limic 2, you could get a maximum of up to almost 12 gigabytes per second, which is almost the maximum memory bandwidth you can get out of a thread accessing memory. So the change is very significant. Using CMA, you can see that Mbappage has made some inroads into improving their on-node bandwidth even without this support. So the blue line looks even better than the old stack, getting up to 10 gigabytes per second, but still for intermediate size messages. So this change you see here is probably the eager limit. So this is all sent through the eager limit protocol, and anything above that is probably coming over through a rendezvous protocol. That's why that kink appears there. But at any rate, if you enable CMA for these messages in this area in between, about 100 kilobytes or so, you can get much, much higher memory bandwidths, also almost hitting about 12 gigabytes per second. And in the future, we're more likely to support CMA or KNM than we are to support LIMIC, because LIMIC requires an extra daemon to run on every node, and LIMIC has less checks for operation safety than CMA and KNM have. So it is more likely that a code would fail with a segmentation fault if it's running out of memory if you're using LIMIC than if you're using CMA or KNM. Or at least with CMA and KNM, you would get an error that is a little bit more descriptive. Notice that the usage of these guys only makes any difference for large messages. If your message is very small, they're not going to be in use anyway, and you're going to depend more on latency than on bandwidth, so you don't really care about this too much. I'm going to run over this fairly quickly because I don't have much to say about collective operations. Essentially, collective operations, I'm sure you were told this morning, are operations that touch all or most of the tasks in a communicator group. The reason they're problematic is because they're not point-to-point. They don't involve only two tasks. They involve many tasks, possibly all of them, and multiple connections between multiple tasks, which makes the whole communication a lot more complex. You can always reproduce these by using point-to-point exchanges, but it can get very, very messy. And to make it efficient, you would have to spend a lot of time in it. So if you have to use collectives, don't try to do your own broadcast. Just use the ones provided by the libraries. But keep in mind that they don't scale particularly well with the number of tasks. So if you can rearrange your code to minimize the use of collectives, you should do that, because that's going to be a massive bottleneck when you're trying to scale to a very large size. And I have about 4 slides more, and we'll be done with this part. So communicators and groups, the only thing I want to tell you about communicators and groups is this on the next slide, is that if you're using collectives that communicate to everybody on your MPI-COM world, but don't necessarily have to exchange information with everybody, then there's a better way to do that. You can create a subgroup and a subcommunicator that only contain the tasks that need to be aware of that information. And so when you execute a collective, you execute it associated to that communicator, and only a subset of your tasks will be involved. What that does is that lowers the complexity a lot, that makes sure that messages can be established faster and your throughput will be faster. So think about this when you're writing your code. If you don't need to communicate with everybody, don't, right? And I just like to put this slide with just very simple 6 steps that allow you to create a subcommunicator in a subgroup. And I have, let's see. Okay, not all is lost. I have 6 slides left. We can make it. Using MPI with the PHY. So something a little bit different in Stampede, or very different in Stampede, is that we have these PHY coprocessors. And when you start talking about communicating with MPI and communicating on top of that with a coprocessor, things get fairly complicated. If you think about doing homogeneous MPI runs with 2 sockets, then the situation is fairly simple. On a node, you have 3 ways of communicating. You can communicate with yourself, you can communicate with your neighbor, and your neighbor can communicate with yourself or with you. That's it. You know, there's essentially 3 paths. When you have 2 sockets, things start getting a little bit more complicated, because on top of the local node communication, you have all the possible path combinations outside of the node. And then you go and you add PHYs. And this is what happens. So just on node, you will have all these paths. So you have at least 4, 8, you have 10 different paths that you can take on a single node to go to mic. And then as soon as you start going off node, the number of paths becomes completely crazy. So it's a very, very complex situation to handle for the MPI stack. It's even a very, very complex situation to handle from the hardware point of view. CPU to PHY communication is not completely symmetric. So depending on where the message is initiated, you will get a different bandwidth. This has multiple reasons. Some of it is because of the read and write rates of the controller in the PCIe that Sandy Bridge has are not the same. Also, the threads in the mic are much weaker than the threads in the host. So when you're using one thing with a single thread, you get delays compared to running on the host. So what happened after a little bit of time is that both Intel and the Mbapich 2 developer team, and now the OpenMPI developer team is starting to support this too. They've developed something called the proxy, which is a system by which calls that would be initiated on the mic are essentially captured, and they're going to be initiated on the host. And I'm being very, very gross here in the way I'm describing this, but the idea is that you're going to avoid this delay or this slowdown that happens if you don't use the proxy. Important for you to note is that the proxy is not enabled by default in the Intel MPI stack in Stampede. So if you want to use the proxy, you need to use this line that I have down here. You would have to do export IMPI Apple provided list and put this. And there's a third element that you could add there, but I have not added it because in the past, we've seen some stability issues and it has not changed the performance a bit.
Is it true that writes from the mic use the proxy, but reads don't really?
So that sounds likely. I don't know exactly how the proxy is implemented, but that sounds likely because of the way the controller does the reads and the writes. That makes perfect sense. Yeah. I don't have, so I used to have a set of figures here with the bandwidths for messages initiated on the mic and messages initiated in the host. But now I'm just giving you numbers here for a ping pong exchange. So you will see the effect averaged out. But essentially you see that both for Intel and Mbapich 2, if you don't use the proxy, essentially the maximum bandwidth you can get is about 1 gigabyte per second. It's a little bit more on node for Intel MPI, it goes to 1.5, but it's still a very poor performance. However, once you engage the proxy, you can get up to 4 gigabytes per second across mics, across remote mics, or almost 4.5 if you're doing mic to remote host. So it's still short of the 6.2 gigabytes per second you can get point to point between the hosts, but it's 3 times, 4 times what it used to be in the past. And it's at a point where MPI across those two devices makes sense. Mbapich 2 mic is even better, particularly the 2.0 version that we have not deployed in the system yet because we've been testing until recently, but I should have a version I can deploy in a few days because I already talked to the developers. With Mbapich 2 mic 2.0, with proxy enabled, mic to remote mic gets 6 gigabytes per second, which is extremely good. And mic to remote host gets 6.5 gigabytes per second, which is almost saturating the PCI Express bandwidth. So enabling the mic is critical for codes that run symmetric. So if you're just doing an offload code, this does not affect you whatsoever. But if you're running MPI tasks on the mic, you should pay attention on what's the best way to run with the proxy enabled. And I've run over like 8 minutes, but we're finally in the summary. So essentially, if you want to look at optimization, you want to look at scalability, the main things are you need to document what you're doing, you need to try to make it automatic, and you need to be able to control and repeat your control experiments so that you can be sure that what you measure is the right thing. The way I've defined scalability is essentially based on loading balance and communication, because I think that's what makes most sense in terms of scalability. But remember that file I/O it's also a form of communication in a parallel file system. So that's going to be also a very big bottleneck for large scale executions. I've gone on about using memory effectively plenty of times. Just remember, sometimes it's worth it just recomputing and try to write your code in a way that accesses memory continuously. And then my recommendation when you see a performance that you don't expect, a performance that is too low, is look for the most common problems first. Look at file system I/O. How often are you writing to disk? Do you need to write that often? If you don't, reduce that. Go to the next part. Network latency. Do you know what the size of the messages your code is changing? No, use MPIP, use IPM, determine how large they are. If they're very short, try to do message aggregation. Look at network bandwidth. Are you saturating the network? Do you have really large multi-megabyte messages that you're changing very rarely and you still have scalability problems? Look into using a different algorithm. Look into using asynchronous communication to overlap the messages changes with work that can be done in your device. Do you have an unbalanced workload? You can monitor idle times for different tasks and try to figure out if some of them are idle significantly more than the others and adjust the work per task, etc. And this is the last slide. I just want to put a note on parallel IO. And I've said this several times, and I'm sure everybody else at TAC has said this several times, but parallel IO is often a major obstacle in using data efficiently. You can have just multiple accesses to the same file, which will lead to contention. You have limited IO bandwidth, or you might have just the sheer number of files that you're writing is ridiculous. So you have several aspects that you need to consider. You have to consider how many files you want to write. You want to write one file per task. You want to write one file per node. You want to write one file per some subset of tasks. How many simultaneous readers and writers and how many stripes are you going to use? All of these are typically code dependent. So you're going to have to do your own investigation. But typically, my recommendation would be try to use a standard parallel IO library, something like HCF5 or NetCDF, and figure out if you can write multiple files, but each of them is spanning the output from several computational cores, because that will give you a lot of flexibility. Questions? No? Excellent. Thank you. So, whoa. So I have an awesome screen here. It's already broken, I think. All right, so the next part is the lab. So there's a hands-on scalability lab. Please just follow the instructions there and let us know if you have any questions. There are some solutions provided. So take your time to do that exercise. We're going to stop?
Yeah, we'll stop the broadcast.
Okay.
You can still ask questions.
And we're going to stop the broadcast at this point, but you can still ask questions online if you have them.